Can we actually stop a space threat? The reality of planetary defense in 2026. Somewhere out there, right now, a rock the size of a stadium is tumbling through the dark in complete silence. No engine, no pilot, no warning label, just gravity, momentum, and time. And the unsettling truth is this: we don't know where most of them are. We've found the giants. We've mapped the monsters capable of ending civilizations. But the mid-sized killers, the ones that could flatten a city, not a planet, those are still mostly invisible, drifting through a solar system that is far more crowded than it looks from your backyard. So here's the question that keeps planetary defense scientists up at night, and the one we're going to answer tonight, honestly, without the Hollywood nonsense. If something really is coming for us, can we actually do anything about it? For most of human history, the answer was simply no. We didn't have telescopes. We didn't have rockets. We didn't even have the concept that the sky itself could kill you. Ancient civilizations built myths around comets and meteors, omens, gods, punishments, because the alternative explanation, that physics doesn't care about us, was too uncomfortable to consider. It took a 1908 explosion over a remote stretch of Siberian forest, an event now known as the Tunguska Blast, to start nudging humanity toward a different kind of fear. No crater. No meteorite fragments recovered for decades. Just 80 million trees flattened in a radial pattern, shockwaves that circled the globe, and a quiet, growing suspicion that the sky had teeth. Then, in 2013, the universe sent a second, much more personal reminder. Over the Russian city of Chelyabinsk, a meteor roughly 20 meters across, smaller than a 6-story building, entered the atmosphere undetected, exploded with the force of dozens of Hiroshima bombs, and injured over 1,000 people, mostly from flying glass as shockwaves blew out windows across the city. Nobody saw it coming. Not because we lacked the technology, but because nobody was looking in that particular direction at that particular moment. The object had approached from the direction of the sun, invisible against the glare, the oldest blind spot in the solar system. That event did something remarkable. It turned planetary defense from a quirky academic curiosity into a budget line item. Within years, space agencies that had spent decades cataloging distant galaxies and exoplanets suddenly found themselves funding something closer to home. An actual, organized effort to find every large rock that could conceivably hit us, track its orbit with mathematical precision, and, if necessary, figure out how to nudge it out of the way. So let's talk about what planetary defense actually means in 2026, because it is not what science fiction trained you to expect. There is no laser cannon bolted to a space station. There is no missile silo aimed at the sky. Planetary defense, as it exists right now, is built on 3 pillars: detection, characterization, and deflection. And honestly, the first 2 are doing almost all of the heavy lifting. Detection is the unglamorous backbone of the entire enterprise. Across the globe, a network of observatories scans the night sky every clear night, searching for faint points of light that move against the fixed background of stars. Programs with names like the Asteroid Terrestrial Impact Last Alert System and the Catalina Sky Survey sweep wide patches of sky, comparing image after image, hunting for that telltale drift that separates a near-Earth object from a star. When something new turns up, the data flows to the Minor Planet Center, a kind of international clearinghouse that catalogs the position, brightness, and likely orbit of every newly spotted object. Thousands of observations get processed every single month. It is patient, repetitive, unglamorous work. It is also the only reason we have any warning at all. Here's the sobering part. Astronomers estimate they found the overwhelming majority of the truly civilization-ending objects, the kilometer-plus giants whose impact would trigger global climate catastrophe. Those are big, bright, and they've mostly been swept up by decades of survey work. But drop down to the city killer range, somewhere between 50 and 150 meters, and the picture changes dramatically. We've only identified a small fraction of those. They're smaller, dimmer, harder to spot, and there are vastly more of them. Statistically, one of those city killers is far more likely to surprise us than one of the giants, precisely because giants get found and smaller ones slip through the net. This is where the next generation of detection technology comes in, and it's worth pausing on, because it represents a genuine leap forward rather than an incremental upgrade. NASA has been developing a dedicated space telescope, the Near-Earth Object Surveyor, purpose-built for exactly this problem. Unlike ground-based optical telescopes, which essentially hunt for sunlight bouncing off an asteroid's surface, this instrument is designed to detect infrared heat, the warmth that even a dark, sun-blackened asteroid radiates simply by existing. That distinction matters enormously, because some of the most dangerous objects are also the hardest to see. Dark, carbon-rich asteroids that reflect almost no visible light and comets that spend most of their orbit too faint to track. An infrared hunter parked in space, away from the scattering and atmospheric noise that plagues ground telescopes, can pick out these stealthy objects in a way that optical surveys simply cannot. There's also a structural advantage to putting a telescope in space rather than on a mountaintop. Ground-based observatories are blind during the day, blind through cloud cover, and blind to anything approaching from the direction of the sun, exactly the blind spot that let the Chelyabinsk meteor through undetected. A space-based infrared survey doesn't share those limitations in the same way, giving scientists a far more complete picture of what's actually out there, day and night, regardless of weather. Now, finding an object is only step one. The far more nerve-wracking part is figuring out, with mathematical certainty, exactly where it's going to be years or even decades from now. Orbital mechanics is unforgiving in a useful way. Once you have enough observations of an object's position over time, you can calculate its orbit with extraordinary precision, then run that orbit forward through time like a cosmic chess engine, checking whether its path will ever intersect with Earth's. The tools used for this, systems with names like Sentry and CNEOS, continuously crunch the numbers on every cataloged near-Earth object, flagging anything whose probability of impact rises above background noise. And here is something genuinely reassuring, something that almost never makes headlines because good news rarely does. This system actually works. In late 2024, astronomers discovered an asteroid called 2024YR4, and initial calculations gave it a small but real chance, peaking briefly above 2% of striking Earth in December 2032. For a few tense weeks, this was the most dangerous-looking asteroid risk assessment in years, briefly topping the Torino impact hazard scale higher than anything tracked in modern monitoring history. Headlines flirted with alarm. And then, exactly as the system is designed to do, more observations rolled in. As astronomers gathered additional data points, including powerful new observations using the James Webb Space Telescope in early 2026, the uncertainty in the orbit shrank and shrank and shrank again, until the impact probability collapsed essentially to zero. Not just for Earth, but for a brief secondary scare about a possible lunar impact as well. The latest tracking data showed the asteroid would pass tens of thousands of kilometers beyond the Moon. No impact, no drama, just an asteroid quietly continuing on its way. That's the system functioning exactly as intended. Early detection, refined tracking, narrowing uncertainty, and a calm, evidence-based stand-down. No movie-style countdown. No last-minute heroics. Just better data replacing scarier assumptions, which is, frankly, how most real science actually resolves itself. But detection and tracking only answer the question of whether something is coming. They don't answer what you do if the answer is yes. And this is where planetary defense crosses from astronomy into engineering, and where things get genuinely interesting. The headline achievement here, the one that fundamentally changed the conversation, happened in September 2022, when NASA deliberately flew a spacecraft into an asteroid. This was the Double Asteroid Redirection Test, known as DART, and it remains the only full-scale planetary defense experiment humanity has ever actually conducted. The target was carefully chosen. A binary system, two asteroids locked in mutual orbit, the larger named Didymos, the smaller moonlet named Dimorphos, orbiting roughly 11 million kilometers from Earth at the time of impact. Far enough that there was zero conceivable risk to our planet, but close enough to observe in extraordinary detail. The spacecraft itself was almost comically simple. A box about the size of a small refrigerator, weighing roughly 570 kilograms, with no explosives, no nuclear payload, nothing but mass and velocity. It navigated autonomously through the final tens of thousands of kilometers using its own onboard camera and guidance software, distinguishing the smaller asteroid from its larger companion in real time, correcting its own course right up until the final seconds. Then it simply slammed into Dimorphos at roughly 22,000 kilometers per hour and was instantly destroyed. The goal wasn't destruction for its own sake. It was momentum transfer, physics' most basic, unglamorous, reliable principle. Hit something hard enough in the right direction, and you change its velocity even if only by a hair. Before impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After impact, that orbital period shortened to 11 hours and 23 minutes. A difference of 32 minutes. That might sound trivial. It is anything but. It represented a far larger orbital shift than scientists had even dared hope for going in, and crucially, it proved that a relatively small, unmanned spacecraft really could alter the path of a solar system object through nothing more than a well-aimed collision. Part of why the shift was so dramatic comes down to something scientists call the momentum enhancement factor. When DART struck Dimorphos, it didn't just transfer its own momentum. It blasted a cloud of rock and debris off the asteroid's surface, and that ejected material carried momentum of its own, recoiling in the opposite direction like the discharge from a rocket engine. Research has since shown this ejecta effect roughly doubled the total push delivered to the asteroid compared to the spacecraft's impact alone. In other words, the asteroid essentially helped redirect itself. And the story didn't end there. More than 3 years after impact, researchers published new analysis showing something even more remarkable. The collision didn't just change Dimorphos's orbit around its companion asteroid, it measurably altered the entire binary system's orbit around the Sun. The shift was tiny, a fraction of a second over a journey lasting more than 2 years, but it marked the first time in history that a human-made object measurably changed the path of a natural celestial body around our star. Scientists described it as proof that even a minuscule nudge, applied early enough, can compound over time into something significant. Given years or decades of advance warning, a small velocity change applied today can translate into thousands of kilometers of separation by the time an asteroid would otherwise have reached Earth. This single mission validated what's known as the kinetic impactor method, essentially cosmic billiards, redirecting a threat through controlled collision rather than destruction. It is currently the most mature, most tested, and most trusted tool in humanity's planetary defense arsenal. But it's not the only tool, and it's worth understanding why, because kinetic impact has real limitations. DART worked beautifully on Dimorphos partly because Dimorphos is what scientists call a rubble pile, a loosely bound aggregation of rock and dust held together mostly by weak gravity rather than solid structural integrity, the kind of object that ejects material easily on impact, amplifying the push. Not every asteroid is built that way. Some are dense, solid, monolithic bodies that might respond very differently to a high-speed collision, potentially absorbing the impact with far less momentum transfer, or in a worst-case scenario, fracturing in unpredictable and dangerous ways rather than simply deflecting. Until humanity tests a kinetic impact against a solid, non-rubble pile target, that uncertainty remains very real. This is exactly why scientists keep insisting, almost as a mantra, that we need more than one technique in the toolbox. Which brings us to the second pillar of validation currently underway. The European Space Agency launched a follow-up mission called Hera in October 2024, and it's now making its way back to the very same binary system that DART struck. Hera isn't going to hit anything. It's going to do something arguably more valuable. It's going to study the crime scene in forensic detail. Where DART told us how much Dimorphos moved, Hera is designed to tell us why, measuring the asteroid's internal structure, its mass with far greater precision, the size and shape of the crater DART left behind, and the physical properties that determined exactly how the impact unfolded. Scientists openly admit they still don't fully understand the internal architecture of these objects. Are they uniformly porous? Are there structural differences between Didymos and its smaller companion? Those answers matter enormously because they determine how confidently we can apply DART's lessons to a different asteroid, made of different material, structured in a completely different way. Hera is expected to arrive at the system around 2026, closing the loop on humanity's first deflection experiment with the kind of detailed follow-up that turns a single data point into an actual predictive model. So kinetic impact is proven, but it has a fundamental limitation that has nothing to do with engineering time. DART-style deflection works best when you have years, ideally decades, of advance warning. The earlier you nudge an asteroid, the smaller the push needs to be, because that tiny velocity change has more time to compound into a meaningful change in position. Catch a threat early enough and a velocity nudge measured in fractions of a millimeter per second, applied a decade in advance, is enough to turn a direct hit into a clean miss. But catch it late, months rather than years, and the math turns brutal. You'd need a far more violent intervention to achieve the same deflection in a fraction of the time, and a single kinetic impactor may simply not be powerful enough. This is where the conversation, uncomfortably but necessarily, turns to nuclear options. It's not the plot device Hollywood imagines. Nobody is proposing to blow an asteroid into 1,000 smaller, equally dangerous fragments raining down on every continent simultaneously. The actual concept under serious study is far more restrained. Detonating a nuclear device near an asteroid's surface, not on it, at a carefully calculated standoff distance, so that the explosion's energy vaporizes a thin layer of surface material rather than fracturing the object outright. That vaporized material blasts away from the asteroid like a rocket exhaust, and the recoil pushes the remaining asteroid in the opposite direction. Essentially the same kinetic principle as DART, but using radiation pressure and ablation instead of brute mechanical force, with vastly more energy available per kilogram of spacecraft. Why does this matter? Because for very large asteroids, or for threats discovered with very little warning time, a nuclear standoff deflection can deliver an order of magnitude more deflection energy than any kinetic impactor we could realistically build and launch in time. Space agencies have been explicit that this remains, by policy, a last resort, not because the physics doesn't work, but because of the enormous legal, political, and technical complexities involved in using nuclear devices in space, the verification challenges, and the simple fact that you only get one attempt to get it right. But the official planetary defense doctrine of the world's leading space agencies treats continued research into this option as essential, precisely because it may someday be the only tool capable of responding fast enough to a late-detected, large-scale threat. There's a quieter, slower alternative too, one that sounds almost too gentle to work, and yet is mathematically sound: the gravity tractor. Instead of hitting an asteroid at all, you simply park a spacecraft nearby and let gravity do the work. Even a relatively small spacecraft has mass, and mass exerts gravitational pull, however faint. Hold that spacecraft in a stable position near an asteroid for months or years, using its thrusters to counteract the asteroid's own gravitational pull on it, and the asteroid will slowly, imperceptibly, be tugged toward the spacecraft's position, altering its trajectory by a tiny amount that, again, compounds over time. It's slow. It requires enormous patience and a very long warning window. But it offers something the violent methods can't: total precision and zero risk of fragmentation, because nothing ever touches the asteroid at all. For smaller, well-characterized threats found early, it remains an elegant, low-risk option still very much on the table. So where does that leave us, practically, in the year 2026? It leaves us with a defense system that is, honestly, better than most people realize, and more fragile than most people would like. The encouraging side first. We have, for the first time in human history, actual flight-tested proof that asteroid deflection works. Not theory, not simulation. A real spacecraft hit a real asteroid and measurably changed its orbit, twice over, both around its companion and around the Sun. We have a functioning, continuously updated global tracking network that has already caught and correctly resolved a genuine impact scare, walking 2024 YR4 back from a frightening probability to a confirmed miss using nothing but patient observation and better data. We have a dedicated infrared space telescope in active development specifically to close the detection gap on the smaller, darker objects that current surveys still miss. We have an international follow-up mission en route right now to turn a single successful experiment into a generalized, repeatable science. And we have multiple deflection strategies: kinetic, nuclear standoff, and gravity tractor, each suited to different warning times, different asteroid compositions, and different risk profiles, rather than betting everything on one approach. Now the uncomfortable side, because a documentary that only tells you the good news isn't being honest with you. The single greatest vulnerability in the entire planetary defense system isn't technological. It's temporal. Every single method we have, without exception, becomes dramatically less effective the less warning time we have. DART-style kinetic deflection wants years to decades of lead time. Nuclear standoff deflection buys back some of that lost time, but it's still not an instant fix, and it carries political and engineering hurdles that have never been tested in an actual emergency. Gravity tractors want even more patience than kinetic impactors. There is currently no method, none, that could reliably deflect a large, late-discovered object with only weeks or months of warning. If something genuinely dangerous announced itself with a short fuse, our best response options would shrink dramatically, possibly down to evacuation and disaster mitigation rather than deflection at all. which is precisely why governments are quietly developing exactly that kind of contingency planning alongside the more exciting deflection research. The second uncomfortable truth is detection coverage. We've done remarkably well finding the giants, and the giants, ironically, are also the rarest. The objects most likely to actually threaten a populated area in our lifetimes are the mid-sized ones, the 50 to 150 meter range, the Chelyabinsk class, and larger objects that are simultaneously common, dim, and still mostly unmapped. Closing that gap is precisely what the next generation of space-based infrared detection is designed to do, but until that telescope is fully operational and has had years to build its catalog, there remains a real, quantifiable population of potentially hazardous objects we simply haven't found yet. Statistically, the most likely scenario isn't a known, tracked asteroid we fail to stop. It's an undiscovered one we don't see coming until it's already in the sky. Exactly the Chelyabinsk scenario, just potentially larger. And there's a final piece worth sitting with because it reframes the entire conversation. Planetary defense isn't really a single mission with a finish line. It's an ongoing relationship between humanity and an indifferent universe, one that requires sustained funding, sustained international cooperation, and sustained patience for a threat that, by its very nature, might not materialize for decades or might announce itself with almost no warning at all tomorrow. It's hard to keep funding agencies focused on a problem with no fixed timeline and no guaranteed payoff. And yet that's exactly the discipline this field demands, because the cost of being unprepared, even once, dwarfs the cost of decades of careful, patient watching. Here's the conclusion worth carrying with you. We are, right now, in 2026, living through the first era in human history where the answer to "can we stop a space threat" is a genuine, evidence-based yes with conditions. Yes, if we see it early enough. Yes, if our detection networks keep expanding fast enough to close the gap on the smaller, darker objects still hiding in plain sight. Yes, if the international cooperation that built DART and Hera continues rather than fractures. And it's worth remembering what makes this story genuinely remarkable. Every other mass extinction event in Earth's history happened to creatures that had absolutely no say in the matter. Dinosaurs didn't get a vote. They didn't get a telescope. They certainly didn't get a spacecraft capable of nudging a 600-meter rock off course. We do. For the first time in 4.5 billion years of this planet's existence, a species living on it has built the tools to see an extinction-level threat coming and actually do something about it. That's not science fiction. That's 1995 meter-per-second momentum transfer, infrared photon counting, and decades of patient, unglamorous orbital mechanics, conducted quietly by people who understood that the most important headline is the one that never has to be written. The sky still has teeth, but for the first time, we're not standing underneath it unarmed. We're watching, we're calculating, and when the moment finally comes, however many years or decades from now, the question won't be whether we can act. It'll simply be whether we acted early enough. And that, more than any laser or warhead, is the real frontier of planetary defense. Not the weapon, but the warning.